What was that?
17.
17 is 2 times 8 plus 1. So how about, I'll throw out one, 23.
That's a good one.
Because 23 is 2 times 11 plus 1. Can anybody think of another?
Because one of them is weird.
So another one that we could think of, or that could work, might be 79. Now, does anybody for sure know that 79 is prime? I think it is. Let's do some tests here. Okay, that's 5, which is good. And then how about like 9? That's 9. That's good. 15. Oh, yep, that's good. 23. Yep, that's good. Okay, so it's prime. What I just did is a probabilistic primality test. This probabilistic primality test is making use of a little thing called Fermat's little theorem. Fermat's little theorem states that if you have a prime, you can do a to the p mod p. Actually, it says a to the p minus 1 mod p equals 1, right? And so if we do a to the p mod p, we'll get 1 times p. So I just did that for a bunch of different numbers, and it all came back with the same number, probably prime. There are numbers for which this primality test succeeds for every single number you put in. I believe those are called Carmichael numbers. But I might be wrong. I might be confusing it and getting the name wrong and switching it with something else. But there are a small number of numbers for which that test succeeds for every single number that you throw at it. And every a, it still gives you 1. They are called pseudo-primes. And there's a more complex probabilistic prime test called Rabin-Miller that does a better job where you can actually detect that Carmichael numbers are not prime. But that's not the focus here. So we have 23 and 79. So I'll do RSA first, even though it's the more complicated of the two algorithms. It's the one that everybody probably knows better. So in RSA, you would have 23 and 79 would be your 2 primes. That's your private key. Your public key is those 2 primes multiplied together. In this case, 18, 17. So for various reasons, we need a funny algorithm that let's see here. What one do I need for that one? Yes, that's the one I need. So import. So I made an algorithm called extended Gcd. I don't have a very good docstring for it. Now, there is an algorithm called Gcd, and, yes. And that one has a nice docstring. And everybody knows about the Gcd algorithm. Does everybody know what Euclid's algorithm is for finding the GCD? Does anybody not know Euclid's algorithm for finding the GCD? Okay. So here's how Euclid's algorithm for finding the GCD works. So you start with let's pick a number, let's build something up. Times 3 times 7. And then we'll have 2 times 5 times 7, right? So what's the GCD of 63 and 70? So what you, right. But with the way you do it, or the way this algorithm works, because it's supposed to work for any size number. You can just eyeball this one and make a guess because you can sort of factorize it in your head and figure it out. And also, too, the factors are sitting right there because I built it out of the factors. But if you wanted to know without knowing that, and they were huge numbers, this algorithm will give them to you. So the way you do it is 70% 63. That gives you 7. And then you use 63% 7. That gives you 0. Well, 7 is the GCD. And we can take arbitrary numbers like 237, that's likely prime. We'll take 236. We'll pick something where we know there's a GCD that's not 1. Pick 236 and 422. So that has a GCD of at least 2, and maybe something else. So then we can do 422% 236, get 186. 236% 186. And you get 50, 50, or 186% 50. That's not what that's supposed to do. Oh, that's what that's supposed to do. There we go. And you get 36, 50%, 36. So it can take a few steps. 14%, 8. By now we can tell the answer that we're going to get out of this is 2. But you see how it sort of steps its way down to 2. And then once you get 6%, 2, 0. So 2 is the answer.
Sorry, how did you select 422?
I just
Okay.
pulled it out of the air. I picked something that was divisible by 2 so that the GCD would not be 1. That was the only criteria. So this algorithm can find the GCD of any 2 numbers, and it takes on average about something related to the log of the size of the, log of the number, number of steps to get it done. So the extended GCD algorithm does the same thing, except on the way, as it's doing that, it looks really complicated, but all it's really doing is you have this equation down here, and we're finding the GCD of 23 and 15 for some reason. Well, yes, I'll explain why those 2 numbers soon. So, you start out with the equation 23 is equal to 1 times 23 minus 0 times 15, and 15 is equal to 1 times 15 minus 0 times 23. And then you just subtract the equations from each other and multiply things and keep sort of those equations in mind. And then at the end, you get what you had to multiply 15 by and what you had to multiply 23 by to make sure that the difference was 1.
Is this like a sieve?
No. So do you know why the GCD works? Why the GCD algorithm works? So think of your 2 things. You have your 2 numbers. Think of them as like, what was that?
That goes back to high school math. I can't remember that proof.
Right. But there's a nice graphical one that I've seen. And so we can go for the graphical one. So your number is composed of these equal-sized chunks of some unknown divisor, right? Because that's what it means to have a factor, right? Because the factor is some integer number times some other integer number. So you have this integer number, whatever it is, a, and you have like BAs, B times A. That's supposed to be an asterisk. I guess it looks sort of like a spider, but it's supposed to be an asterisk. And then you have like another number where you have some number of A's. We'll say it's just 3 of them. 1, 2, 3. Oh, nope. We should make it 4 of them to make it a little more interesting. So here we have C times A. That's supposed to be a C. So C times A. So all you're doing with GCD, when you do the remainder, you're sort of figuring out how many times can you stuff this one in here. In this case, you can only stuff it once. And then you get these 2 remaining ones as sort of your remainder. So then you have your remainder are the 2 A's after you subtract sort of like, this is the C times A part. So those are the 2 A's that are left. And so then you find out how many times do these go in here, and you discover, in fact, that I made a mistake in that, in fact, A is not the biggest factor. It's 2 times A that's the biggest factor, because you can fit the 2A in there twice. So whatever A is, 2 times A is the biggest common factor. And that's how this works. Basically, the remainder will always have the factor that you're looking for in it. And so you're just chopping things down using the remainder until you get to just the factor you care about. That's how GCD works. all extended GCD is doing is keeping track of, like this is keeping track of the remainder. Extended GCD also keeps track of how many times each one of these fit in as you were chopping it down. So that at the very end, you actually find out what you had to multiply the two sides by to get a particular result. If it's 0, of course, it's very uninteresting because then you just multiplied it by the other side divided by the greatest common divisor. But if it's 1, it's a very interesting result for reasons I will get to shortly. And so that's what extended GCD is all about. And as you can see, I sort of have the equations written out. This is actually available on a website. OSDN, like here, as a mercurial repository because I'm fond of mercurial. So you can actually, if you want to see this code that's not on this screen, you can grab it from here. And mostly I did this because this is not too hard to write, but it's complicated enough that it's really easy to make mistakes. I didn't want to have to write it all in front of you. So yes. And as you can see, essentially we're keeping track of the two sides, and as we're chopping it down, figuring out how many times we have to multiply each side by, we're kind of keeping track of that through each step. Does anybody want me to go through all of the steps for this particular example here, for like 23 and 15?
I think I missed a conclusion somewhere. You're finding the common
Greatest common
divisor
divisor.
between 23 and 15.
Right.
And what does that get you?
Well, I'm not only finding the common divisor, I'm finding the numbers that I have to multiply both 23 and 15 by to get a difference of 1. And that does get me something really important that I will get to in a bit. And that's the point of extended GCD versus GCD, is that it gives you those numbers. And I will demonstrate here. So minus 13, so 23 times minus 13 plus 20 times 15 will be 1. If we cared about 23 here, then we would also discover that if we did 10 times 23% 15, oh. No. How does that work now? So we have 20 times 15. Oh, that's right. 2 times 23% 15. There we go. And on the other side, we would have 20 times 23% 23. Yes. Is that how that works? Oh, I know. No, that's not. Oh, anyway, I know how I will use it later. So, we have our two primes back here. There we go, 23 times 79. So we're looking for the math that extended GCD, or num theory utils, yes, that's right, dot extended GCD of not 23 and 79, we're looking for 22 and 78. Actually, we're looking for 22 times 78, and then we're picking something like 3. Now we know 22 is prime minus 1, and 78 is prime minus 1. So 23 and 79 minus 1. And then 3 is just a number we picked. Has to be, it could be anything. It's best if it's prime. And so there are different reasons to use different size numbers. If you're doing an encryption key, having it be small is good. If you're doing a signing key, It's not so important that it be small. But it does have to not divide 1817. Sorry, no. It has to not divide 22 times 78. And so this GCD has to be 1. Let's not see here. So let's see. Nah, that's not the right one to do. Okay, let's work this out here. So we're getting, oh, they have a common factor. The GCD was, so let's go back up here and pick 23 and 47. Okay, so 1081 is our public key. Now we'll do this all over again. 22 minus 1, 78, or 46 minus 1, 47 minus 1, 23 minus 1, that's right. 45, no, not 45. So 22 times 46 is 1034. So 1032 times 3%, 1034. That isn't the right way around. So 1032 or 1034 minus 675. Okay, this one is supposed to work. So 2347, what am I doing wrong?
22 times 47. You did times 47.
22 times 46. Oh, that's what I'm doing wrong. Okay, thank you. So again, this time 10 times 3. Okay, that wasn't the right way around. So 12 minus 675. Oh, you're right. So many things that I have to remember to change. Okay. So 1012 is the right one. We want percent 1012. Then we want percent 1012 minus 675. That one wasn't the right one. So 1012 minus 2 times 3%, 1012. No. I'm doing something wrong still. Okay. We've got this. We've got 22 times 46. Now is 1012. The GCD is 1. Something times 1012. So 675 times 3 is 2025. There we go. There we go. So 675 is the thing that we want. So let's pick a message.
Sorry, I don't understand the extended GCD result. What are the 3 numbers there?
So the last number is the GCD.
Okay.
So what we want here is minus 2 times 1012 plus 675 times 3 is 1. So that's what it's giving us. I need to have it print the output in a better format to make it more obvious exactly, because what I'm looking for, that I'll talk about later, is I'm looking for the multiplicative inverse of 3, which that's a word that I don't expect anybody to get, or a phrase that I don't expect anybody to get at this point in time. But that's what I am looking for, is the multiplicative inverse. And so I just play around with the numbers that I get out until I find out what the multiplicative inverse is. I could actually fix the extended GCD to just tell me what the multiplicative inverse is. Yes, but I haven't.
And by multiplicative inverse, you mean within the context of the modular arithmetic of
Right.
12, right?
So basically, we're looking for what we can multiply 3 by to have a modulus of 1 when divided by 1012. And that is the multiplicative inverse of 3, mod 1012. As I said, whatever that means. So we'll call our public key, and we'll call our public key 23 times 47. We'll call our private A equals 23, 47. So we had sort away. So let's pick a message. It can be any number that's less than 1012.
As a message?
As a message. Any number.
413.
420.
900 was the first I heard. So 900 times, or 900 to the power of 3% 1012 is 740. Right? So now that's our encrypted message, is 740. So let's try decrypting it. This actually is probably going to be a very, very large number, and I don't trust Python to do this correctly, to like optimize it, because Python doesn't optimize. So Python actually has this nice function for various reasons that already does this. X star y % z. So we're going to do that. We're going to do 740, 675, 1012. And that's equal to 740 star tar 675% 1012. What am I doing wrong? 23 times 47. Oh, that's what I'm doing wrong. Sorry. We'll try this again. 900% private key. There we go. Now, 625 and in this particular case, 1081. There. Much better. Public key, sorry. Yes. So actually, I should rename this. And we'll do it again, just to make it clear. And then this one. So there. Now, that means 675 had to be secret. But you notice how we were able to derive 675 by knowing what the two values that went into our private key were. We derived 675 because we knew that the two primes were 23 and 47. We had to multiply 22 by 46. In order to know that it was 22 and 46, we had to know that we started with 23 and 47. So in order to figure out 675, you have to know what the two primes are that go into your public key. But the 3 can be public. In fact, the 3 is public. So part of the public key is actually the exponent you expect people to use when they're sending you a message. Does this make sense so far? Like, you've seen the RSA algorithm work. Does this look like the RSA algorithm to you? Yes.
Yeah.
Yeah, because you have basically M star star E is the 900 times 3 thing. So, you know, M would be equals 900, E equals 3. So, you know, M star star E % public key. That gives you your encrypted message. And then you have So, and then you have and 675 is a magic thing based on E that we derived with this extended GCD thing, and the prime is -1 for some unknown reason. Okay, so that's RSA, and that's how it works. The magic happens in the fact that you know to use the extended GCD algorithm in the way that you do, and the fact that you know that you should be using 22 and 46, that you should be using the prime -1. And there are some very good reasons for that, and they have to do with group theory. But I'm not going to get into them right now. That's what I intend to get into in a bit. So the next thing to talk about is Diffie-Hellman. Luckily, Diffie-Hellman is a little bit easier. And in Diffie-Hellman, you really, really want to have primes that are of the form 2 times p plus 1. It's not as important for RSA. The important thing for RSA is that the factors of prime -1 are not the same as the exponent that you're using. But for Diffie-Hellman, it's really important that the prime that you choose as the basis for your Diffie-Hellman group is of the form 2 times p plus 1. So here for Diffie-Hellman, Diffie-Hellman isn't for sending. Does anybody know what Diffie-Hellman is for?
Key exchange?
Yeah.
The initial key change for
Right. So the goal of Diffie-Hellman is not to send a secret message. The goal of Diffie-Hellman is for two people to agree on a number without anybody in between being able to tell what that number is. And that number is then becomes a key that you use usually for symmetric encryption, for like AES or something like that. And so that's the goal of Diffie-Hellman. It's not to send a secret message. It's just to both of you agree on a secret number. So we'll start off with Alice and Bob will pick an exponent. Alice's exponent, we can pick anything that's not 2, or we'll pick 47 as our basis prime. So Alice can pick an exponent that's anything that's not like 2 or 23. So anything. Anything. What was it? 19. 19. So Alice's exponent is 19. Bob's exponent is anything, again, anything that's not 2 or 23. 50, except it has to be less than 47.
Oh, I was going to say 47.
Yes. 43. Okay. So then we will take, we have our Diffie-Hellman prime equals 47. Then the other thing that we have to decide on is a generator. And this generator is one that both Alice and Bob use. It's called a generator for a reason, but we'll pick 4. So here's what Alice sends Bob. When Alice and Bob want to have a talk, right? Alice and Bob want to agree on a secret. So Alice sends something to Bob. Alice takes G ** 19 %47. And these are small enough that I don't feel the need to use the POW thing. So Alice sends Bob 9. And actually, I should have used Alice exponent here, there. And we should use DHP here. Okay. Now Bob sends Alice this. Okay, so they each sent each other some weird random number, 9 and 36. Well, once Alice gets her 9, what Alice is going to do with the 9 is she is going to take 9 ** BE, or no, * AE %47, DHP. Right? So she's going to get 42. And Bob is going to take his, the number that Alice sent him. He should have gotten 42 too. Now let's see, why did this not happen? So G star star AE percent DHP is 9. So that's to the Alice's exponent. 9 to the, oh, I did it the wrong way around. It should be 9 to the Bob's exponent, and it should have been 36 to the Alice's exponent. There we go. Sorry. So here's what we're trying to do. Both sides are trying to compute. Both sides are trying to compute G star star 19. No, G star star AE star star BE percent DHP. Right? That's what both sides are trying to do. But one side is going to compute it in this direction, and the other side is going to compute it in that direction. So one side is going to send this, and the other side is going to send that. And then they will each be able to agree. And you can easily see, like, this is on a symmetric equation. They are both going to get the same result. And in order to figure out what Alice's exponent is given 9, you have to solve a problem called the discrete logarithm problem. You basically have to find the exponent in a finite field given a number. And that turns out to be really hard. It's really easy in this case. You could just generate what they all are without a lot of difficulty. You know, there's not that many numbers. But when your numbers are in the size of 128 bits or 10,024 bits, it starts getting really, really hard to solve this problem. So that is how Diffie-Hellman works.
Question on that. So, Diffie-Hellman, you do have like a pre-shared key between the two, correct? No, it's just completely just for random.
Yep.
It's unknown.
Except for the generator, right? Like,
Well, the generator and the DHP, the Diffie-Hellman prime, are public parameters that a lot of people use. A lot of people will use the same because there's some interesting, weird little mathematical quirks about the generator and the DHP. And so you want them to be chosen by some authority that's in fact done the work to figure out that you have good generators and good Diffie-Hellman primes. But those are public parameters that get used by a whole lot of people. But the exponents themselves are the secrets. And they aren't shared. So, in fact, that's what Diffie-Hellman is for being able to come up with a agreed upon shared key. Okay. So, why do these things work? Like, I mean, it's clear looking at the math for Diffie-Hellman why, I mean, it looks obvious why it should work. Like, those things are commutative operations. You should be able to switch them around. But why does it turn out that the discrete logarithm problem is secure? And RSA, it's kind of a mystery why it works. Why are we using P, when we have our prime, our public key created by P and Q, why are we using P minus 1 and Q minus 1? What's the extended Gcd algorithm doing in there? Like, those are kind of weird. I remember the first time I implemented, I just did it. And I didn't really understand what I was doing or why it worked. The reason why it works is really interesting. And I'm going to start going down the path of telling you why. So, how many of people here have heard of a group in the mathematical sense? Okay. Actually, another question. How many people have questions about this, about RSA or Diffie-Hellman after my mistake-ridden attempt to show you them?
What do you use RSA for?
So RSA is used for two things. So in RSA, the exponent, as we go way back up here, we chose 3 as our exponent, right? That's a public value that's associated with the key. The public key is in fact composed of 2 pieces. The public key is composed of the 2 primes multiplied together and a public exponent for people to use. And you just publish that. Tell everybody in the world, my public key is such and such. And in fact, usually if you're using RSA, everybody's kind of agreed, you know, for this protocol, everybody is going to use this as their public exponent. It isn't like the public exponent has to be specific to the particular key. Everybody can use the same public exponent, and it's just fine. But the public key has different. So you just publish your public key in the newspaper or whatever. And then anybody can take, I have a private message, a pretty tiny private message because it had to fit, be less than 10,012. For a really large RSA key, your message can be as big as the key is, almost. And so, you know, you pick that big giant message and you just send it to somebody. You take it to the exponent and you send them the result. Able to read log and finding out what it was that you took to the third power to get this value.
When you do.
Right. So RSA, you can actually send somebody a message. Whereas Diffie-Hellman, you don't get any control over what that secret number is, right? It's just a random secret number. Does that make sense? Okay.
Do you use that then as like a password, or like that secret number that is generated? How is that one used?
So if you're using a fairly large Diffie-Hellman prime, what I've done is I've passed the secret number through a hash, like SHA2, gotten 256 bits of stuff out of it, use that as my secret key, for block-based encryption like AES. That's usually what you would do with it. There are schemes to actually use this for doing signatures and stuff like that. I'm not going to get into those here, but that's what the public, what is it called? There's a public signature algorithm that's based on this that GPG supports. Oh, shit. Yeah, it's like that NIST came up with for a long time ago for using Diffie-Hellman to do digital signatures. And so there is a way to do it.
Like a central point that like knows all the.
No, like, so let's look here at the Alice. Are you talking about for digital signatures or for? No. The way you get around that is you get around it in the hash that you're signing as operator.
Signature algorithm, that wouldn't be DSA, would it?
Yes, that's it, DSA.
Because as I recall, the secret trick with the DSA is when they built it, they were still not wanting people to use it for encryption. So DSA has an interesting property in that it works well for signatures, but it's not, unlike RSA, which can do encryption and signing, DSA was designed to make it strong for signatures, but not efficient or effective for encryption, because the government was okay with signing things, but it doesn't want anything to be signed.
Right.
And they to allow you to attest government private.
Yep.
That's what the DSA is.
Yes. I'm sure I've not searched it because I haven't really cared. In my opinion, RSA does say, and that's good enough for me. The way you use I'll explain how you use RSA for signing later. But that 3 and that 75, like the basic thing for RSA is you do RSA percent and then percent private exponent, right? You have public exponent, then multiple message to the public exponent, and then to the private exponent. Well, that looks an awful lot like DSA, right? You can just switch them. And so you can actually have two exponents that you pick. You pick your signing exponent and you pick your message exponent, and you have different private exponents for each. And you just sign things with the signing private exponent, and people can verify by decrypting it to make sure that they get the right value with the public signing exponent. And then they send you a message using the public message exponent, and then you can decrypt it with the private message exponent. So you can use RSA for both sending a message and for signing things, because the algorithm works symmetrically as far as The private, using the private key versus the public exponent for your first exponentiation. So that's why I've never really researched how DSA works. And you're right about why DSA was created the way it is. And it is based on Diffie-Hellman, fundamentally. So if I were going to figure out how it worked, I would start with Diffie-Hellman and then figure out what they did to it to make it into a signing algorithm. Which I'm guessing has something to do with either using the hash for the generator or using the hash as like the public, an exponent somewhere. I have no idea. So now we get to the part with a group. And a bunch of you knew what a mathematical group was. So does somebody who raised their hand, can they tell me what properties, what a group is?
It's a generalization of properties of a set, of kind of operator properties of a set, like inverse, whether or not it commutes.
So a group is a set of things, an operator. That set can be fixed or it can be an operator. Say integers as our example. So that is like the set of all and the operation plus. The reason why that operator is not just a set plus an operation. The operation has to have certain properties too. One result is that if we have like A plus B plus C has to equal A plus B plus C for every single element of your set. So A, B, and C can be any elements of your set, and this has to be true for all of them. And that, of course, will give me an error because A isn't defined, but there we go. So the other property is that for any A, there has to be, there's two more properties. I'll get to this other one first. So there has to be some element, we'll call it E. When you take it with any other element of the set, you get that element of the set back. And that's called the identity element. For addition, that element has to be 0. So anything gives you whatever that thing is. So your identity element. Property that you have that for any element of the set, there has to be some other element of the set such that this happens to be true. So for integers, it's the negative numbers. 1 plus negative 1 is 0. 5 plus negative 5 is 0. So for any integer, come up with some other integer such that when you add the two together, you get the identity element, which for addition is 0. But for multiplication, it would be 1. Right? Because 1 times something is that something. What was that?
Versus multiplication with the integers.
Right, exactly. Right. So multiplication with just plain old integers is not a group because there are no inverses. What do you multiply 5 by to get 1? There isn't anything you can. So multiplication plus the integers is not a group.
So the other implied definition is that for every element in the group in the set that is applied, can't go outside the set.
So that means A plus B has to be where G is our group. So this has to be true as well for any two A in their set. Is a property which is basically a different way of stating the inverse property, and that is saying that for A plus E, for any, if you start with A, some B, you have to get a distinct number for each possible B that you could add to it. Now, that happens to be the same property as the inverse property. Those two are essentially equivalent properties. If you have one, you have the other. So anyway, that's what a group is. And so we have, really good examples of groups. We have integers. Another really interesting group would be if we had integers under multiplication mod a number, a prime. And so I actually built this thing that will do print group table, and then we'll put in for our group list range 1, 8, because we want 1 through 7, comma, comma b, or operator a times b 7. So there. So times 1 is 1, 2 times 2 is 4. You can see each row has every single element in it. Column has every single element in it. This group has one other property that is for some groups, but not, which is that a times b is equal to b times a. Groups of which the commutative property holds are called abelian groups, after this mathematician named something Abel, Norwegian mathematician. I think Nils, maybe? What was that?
It's like kind of like a Sudoku puzzle where every column and row has every number.
Yep, it is a little like that. I've actually thought about seeing if I could think of a way to solve Sudoku puzzles, but I don't. There's some other things that are true about Sudoku puzzles that make it so that it doesn't work. But yes, it's like a Sudoku puzzle. And so, as you can see, it's a group. Let's try 15. Will that be a group? And in fact, no. 1, we get 0 in some of these places. 0 isn't in our set, right? So right away, not a group. But also, too, you notice that for example, for like 3, only multiples of 3 show up. There's no other values that show up in here. And yeah, the reason why that is because 15 isn't prime. 15 has 3 as a factor. So as you're multiplying, as you go up by 3s, you will eventually wrap around, and there's a whole bunch that you'll skip and you'll never get to. Essentially, things, if you're using multiplication mod something that isn't a prime, you'll get false zeros. You'll get zeros that don't look like 0 from the start. And that makes it so that it's not a group, because 0 can't be a member, yes. And 0 can't be. What was that?
So put your range to 18 and use 17.
Okay, I will do that. Poof. And it's a group again. So you can make a group out of any prime under multiplication by just modding by that prime. So, yes. Now, there's actually a whole series of mathematical objects that allow you to apply more and more mathematical abstractions. So you start with a group. And group is one operation, has the properties that I just talked about, like associative property, inverses, all of that. Then you get up to something called a ring. And a ring is a group and another operation. And that other operation we could call multiplication. Like if our original operation for our group was addition, the other operation would be multiplication. And then multiplication, though, doesn't have to have an inverse for a ring. So all of the integers are a ring, because any multiplication of any two integer still leads to an integer that's within the set of all integers. It's just that there's no inverses. So yes, Set of all integers is a ring. And then the step up from that is a field. And a field, oh, there's one other rule that has to be true for the two operations. And so we have to have A times B plus C has to equal A times B plus B times C. So basically, one operation has to distribute over the other. Yeah, A times plus A times C, yes. It's typed, thank you. So that's the other thing that has to be true for things that are a ring. So for fields, you happen to have sort of two overlapping groups. You have your group under multiplication, and then you have your group under addition. Your group under addition is always going to be one bigger than your group under multiplication, because your identity element for addition can't be the same identity element as the identity element for multiplication. Because zero can't be the identity element for multiplication. Now, this is true for integers, obviously, when we're thinking about integers. Like 0 times anything is going to be 0. It doesn't satisfy the group property, right? It actually, there's a really nice and elegant proof that I don't remember that shows that if, no matter what you do, if you have a field, you have to have distinct identity elements for both addition, for your two operations. You can't have the same identity element for both of them, unless that identity element is the only element in the set. So if it's just 0, well, yes, 0 times 0 is 0, 0 plus 0 is 0, it works. But if you have more than one element, you have to have different identity elements for your two different operations. The proof involves showing how the distributed property isn't compatible with having the same identity element for both operations. So let's look at all the integers from 0 to 17 under addition. Does that look like a group? Yeah, it's a group. Right, it's a pretty group. Yes. And there's our thing again of all the integers from 1 to 17 under multiplication. And that's also a group. Not quite so pretty, but it's a group. So we have two overlapping groups where we have different identity elements for each. We have 0 as the identity element for addition. We have 1 as the identity element for multiplication. Therefore, actually, integers mod prime is a field. Once you have a numeric field, essentially all of algebra works on any your objects in that are members of that set. So any algebraic expression that you write, any algebraic equation that you write, holds true for things in that set, as well as it holds true for like rational numbers. So this whole idea is something called abstract algebra. I will look up a book on abstract algebra. There's a really fantastic book that like brings you from the very beginning up through understanding some fairly advanced concepts in abstract algebra. That I think is probably one of the best books I've ever seen on the subject. But that's the whole idea where this comes from. It was invented actually by a guy by the name of Rsa. It was invented as a way to prove that equations of the form like x to the 5th plus x to the 4th plus whatever, you know, ax to the 5th plus bx to the 4th plus cx to the 3rd, don't have algebraic solutions. And so it kind of makes sense that he came up with an abstraction for algebra so that he could prove statements about algebra. Anyway, that's where this comes from. So why is this relevant to what we're doing? So one, you notice primes are involved here. Like, we make our fields out of primes. So it seems like maybe somehow this has some relationship to what's going on in Diffie-Hellman and RSA. Right? Because there we seem to have to choose primes too. Now, the weird thing is, though, is RSA has this thing where you have, like, let's go back up here to 16. You know, this isn't a group, right? RSA has this thing where we somehow care about these things that are prime minus 1 times other prime minus 1, right? And that isn't going to be a group because those two things are by definition not prime, right? So what's going on here? Let's try, in fact, actually, this is the perfect example right here. So let's try list range 1 from x for x in. Because we notice that all of our weird little problems here have to do with things that are factors of 15. Right? Those are the ones that cause this thing to sort of lose its group-like quality. That's where the zeros start coming in. So let's just remove them. Where math, where x, math.gcd, I hope I've imported math, x, comma 15 equals 1. So we're going to pick out all the things that are relatively prime to 15. Let's see what happens when you do that. Well, oh, yes. If well, this is sort of interesting. 2, 4, 8, 14, 1, 7, 11, 13. That looks like a group, doesn't it? How big is this group? 1, 2, 3, 4, 5, 6, 7. It's 8 elements. 8, that's 2 times 4, isn't it? And 15, well, that's 3 times 5. Well, gee, p minus 1 and q minus 1 seem to be showing up here. Let's try this for some other thing that's the multiplication of 2 primes. Let's try 35. So range 1 comma 36. Oh, there we go. This also kind of looks like a group. Does anybody see anything that's clearly not group-like? Does 0 show up anywhere in here?
Not seeing it.
No. So yeah, this looks like a group too. So let's do len x. Actually, for len, I think you actually have to have a list. So let's do list x for x in range 1 comma 36. If math.gcd x comma 35 equals 1. Right. That's 24. Well, 24 happens to be 4 times 6. And 35 is 5 times 7. Interesting. Well, so there seems to be sort of a group hidden in like p times q. And that group seems to be of the size p minus 1 times q minus 1. So there's this really interesting thing, a lot of interest. When people talk about the RSA algorithm, those sort of bring out Euler and in fact, this actually function is this specifically. Euler's view, numbers are relatively prime to your number. And p minus 1 times q minus 1 times whatever other prime you have, we'll call it r minus 1. Whatever primes you have, you just multiply together all the minus 1s, and you get the answer. Euler's totient function starts getting a little bit more complicated if you have multiple prime factors. Like if you have 2 cubed, for example. If we did this for 8, the answer we would get out would be 4. And that's because it's 1 times 2 times 2. Basically, any time a prime is repeated more than once, the second time and the remaining times it shows up, you just use the prime. Whereas the first time it shows up, you use the prime minus 1. So Euler's totient function can't be solved. You can't discover the answer to Euler's totient function without factoring the number that you're trying to discover the answer to Euler's totient function for. So that is part of where RSA security comes from. Is we need to know the answer to Euler's totient function for our public key. But we can't find the answers to Euler's totient function for a public key without knowing the two primes that went into making it up. So why is the fact that those two things make up a group so important? So let's start with exponentiation right here, right? So let's pick exponentiation mod a prime because primes are important here. 2 star star a for a. Let's pick any number. That's we're going to pick our prime as being 11, so less than 11. 7. Or there, right? Oh, forgot one important detail. That's a unique list, isn't it? Well, that's interesting. So the other thing is we happen to know from high school algebra that a star star x times a star star y equals a star star x plus y. So that means multiplication of two numbers is addition of their exponents. We also know that essentially all of algebra works for things that are fields. This identity holds for integers mod p, because integers mod p are a field. So there's sort of an extra group that we get for free out of our field, and that's the group of numbers, the group of powers with plus. So all the powers of something with plus. So here we picked, now there's another thing. We were actually mildly lucky with picking 6 as our base. Actually, you chose 7, didn't you? Ha.
I did.
Yep. So 7 might not have worked so well. No, actually 7 worked just as well. Yes. Let's try a different one. There we go. So notice this is, yes. Notice that we get basically the same numbers repeated twice. So there's also a subgroup in there. If you notice, we'll do set here. That's 10. So there's this thing called Lagrange S Theorem that says, here we go, Lagrange S Theorem. So Lagrange S Theorem for groups. So it's actually very simple. Like, it'll go into a lot of complicated things. Wikipedia is a terrible place to go to for math because the people who edit it have no clue how to make Wikipedia entries that are accessible to people who aren't math people. But
Where is a good place to go for math?
I don't know. I wish I knew. But one thing I will say is that I did look at this beforehand. Yes. And this particular paragraph is very simple. In the mathematics of group theory, states that for any finite group G, the order, the number of elements of every subgroup H that divides the order of G. So subgroups are a group of numbers that all to themselves form a group. So if we were to do, for example, our little thing here, list for x in range 1, so 0, 12. No. We wanted the print, yes. For range in 0, 12. And we don't care about the GCD here. Right? So we're printing out the group table for plus, except, that would help if I actually in here. We're printing out the plus for numbers that are mod 12. And that's a group, right? But there's like little subgroups hidden in here. If you happen to say like add 3 to things. So 0 plus 3 is 3. 3 plus 3 is 6. 6 plus 3 is 9. And then 9 plus 3 gets us back to 0 again. So we could, in fact, if we made a group table, right, of all of the multiples of 3. Why is 1, 4, and 7 showing up in there?
Yeah, doesn't make any sense.
That doesn't make any sense, no.
Because you're doing mod 1.
So 9 plus 9, or
yeah,
9
the
plus
mod
3.
11 at the end.
Oh, that's why. Luckily, nobody looked too hard as to whether the first table was a group, because it wasn't. Yeah, well, no, zeros are okay for addition, but there was 0 twice in a row.
Oh, yeah.
Yep. Yep, that's why it wasn't a group. But there we go. See how this is like a subgroup. Because all of these numbers, the operation on all of these numbers forms another number that's part of the set. Right? Satisfies our group definition. Does that make sense to everybody? Okay. So and you can easily see from how I came up with this subgroup why that subgroup had to be of a size that was a factor of the original group size. The original group size was 12. This group size is 4. And that's because 4 divided by 3, 12 divided by 3 is 4. So we could actually probably come up with another group that's only of size 3. So subgroups always have to have a size that's sort of a factor of the size of the group that they're a part of. And you can see also why this is a subgroup, right? Because it's all internally, everything references each other. So that has implications for our addition for our addition of our powers, right? Because the addition of our powers, the size of that group is going to be 1 less than the prime, because 0 isn't included, right? So the size of that group is going to be 1 less than the prime. Therefore, it's going to have factors. And those factors are going to be the factors of p minus 1. So that's the reason why we got, we did 6, no, which number was it? It was 9. Yes, that's the reason why we got these repeats when we did 9, is because we found a member of a subgroup and went through all the members. It was like adding 3 each time, right, to our things in addition. And so that's why we got this little subgroup here. Is essentially, this is a subgroup of exponentiation. So I think I'm starting to lose people. So let's go for a question period, and then maybe I'll pick this up next month, depending upon what the questions are and whether I feel I've lost people after the questions are over or not. So does anybody have questions?
Is there any way to derive one of the primes? I know you have 2 in your RSA, but has anybody ever found a way to find at least one of them?
Well, if you derive one of them, you derive both.
Have you? Okay, that's
Yep.
what I wasn't sure.
Yeah, because you just have to divide your public key by one of the primes and you get the other.
Sorry, my subconscious was.
Yes. Are people starting to see how this is going to start leading to talking about why RSA works?
It's by all rights, if you look at it at face value. It shouldn't, but it does.
Yes. And the reason why it does is because of these groups that form when you are adding and multiplying your exponents also, except multiplying the exponents doesn't really form a group because the size of your group of exponents for RSA is, you know, p minus 1, or for Diffie-Hellman, the size of your group of exponents would be p minus 1, because you only have one ever, 0. So it's not going to form a group under multiplication all by itself, because you can only form a group under multiplication with primes. But as you saw with this totient thing, if we drop all the things that are factors, and we pick only the things that are relatively prime, we can form this group under multiplication even still. So that's where I'm going with this.
So if you can find the size of a subgroup, it gives you a decent amount of weight towards factoring the two numbers.
Yes. Yes, it does.
That's where you're going, I think, right?
Well, that's also true. That's one of the reasons why you want to be kind of careful, especially with Diffie-Hellman.
I was going to point out with the Diffie-Hellman that, have you seen the paper about the potential issue with actually publishing your Diffie-Hellman parameters? Specifically, if you use the well-known Diffie-Hellman parameters, you can pre-compute 90% of the work ahead of time.
Oh, yes.
And therefore, if you're using the one out of the book, so to speak, an adversary with, you know, a couple million in compute resources can recompute 90% of the work and actually reverse in real time your messages. So you may actually want to, while they can be public, you may want to generate your own if you're concerned about a well-funded adversaries.
Right. Yes, that does make sense. And that would have to do with interesting approaches to solving the discrete logarithm problem. So yes. There's actually other groups other than integers that you can do RSA and Diffie-Hellman in. And that's where elliptic curve cryptography comes in, is you pick elliptic curve cryptography. Yep.
I really don't understand, like elliptic curve cryptography for mentioned a lot, but I don't really understand it.
It's actually a little bit easier to understand in my view than the field.
Well, and the reason why that might be is because the integers, the fact that its numbers isn't distracting you anymore from what's going on.
Yeah, well, these numbers are distracting.
Yes.
You look at 2 points on a curve. Oh, I get that. Right.
Right.
Super easy to look at.
So I don't have the tools to erase it right offhand. But what elliptic curve cryptography does is it creates a curve such that if you pick 2 points on the curve and draw a line through it, that line will intersect another point on the curve. And it turns out that this operation is associative. And of course, 2 points on the curve, another point on the curve, the operation stays within your set. Associative stays within your set. There's always an inverse. You can always go back. So poof, it's a group. And so that operation, taking the 2 points on your curve, drawing the line through it, finding the third point, that is your group operation. And then repeated application of your group operation. That's all exponentiation is repeated application of a group operation. There you go. There's your exponentiation. And so then you can start doing exponentiation on your point operation.
Like this, right? See that point here, point here.
Actually, usually has a
Right. I will draw a better elliptic curve. That's a good parabola.
Wait, but that doesn't hit the curve, like,
doesn't hit it in
again,
3 places.
at very
Yes.
multiple points.
So elliptic curves have a weird mathematical form to them. And I'm not, they essentially are something like y cubed equals x squared plus ax plus b or something like that. That's the formula for them. But what's important here for understanding is they usually generate, if you give them a fairly wide range of different parameters, they'll generate a curve that looks something like this. And as you can see, any 2 points. Now, 2 points on this curve, actually, I think, yes. In fact, 2 points on this curve are going to intersect this curve someplace too. And so that's where your group operation comes in. This point plus that point equals that point. And so then repeated application of that group operation becomes exponentiation. So, you know, this actually what they do is they reflect the point. That's the result point, is the reflected point. And so then you take this one plus this one again. You get that one, reflect it up there. This one plus that one, you get that one, reflect it right down there, so on and so forth. And so that's repeated operation. And then, yep, that's where your groups come in. And it's really difficult, just like the repeated, just like doing exponentiation, it's really difficult to go backwards. The discrete logarithm problem is very hard to solve for elliptic curves, just as it is for integers.
I think this is even more difficult to solve for.
Yep.
Because you're dealing not with integers in this case, but a finite set of all real numbers.
Yes.
Of course, that's the secret trick that Microsoft discovered last month.
Hmm.
You know which make sure that both of the points on the curve. If one of the points isn't on the curve,
Then anything can
it
happen.
breaks.
Yep.
And you get the that certificate story where
There's actually a really interesting elliptic curve-based thing that's been widely promulgated called the ED25519 curve. It's come up with a guy, what's his name? The guy who wrote...
Daniel Bernstein.
Yes, Daniel Bernstein. He wrote QMail, among other things. QMail, the mailing system that essentially had one existence. So it's also really inscrutable to read. He writes code that's really hard to read that doesn't break. But he came up with this.
I think I just got that.
Yes, I've heard that too.
Well, he's the classic open source hacker who makes brilliant work that kind of has to do with.
Yes.
He's not the only one, maybe.
Oh, there's so many.
So it's just it's a curve with some particular parameters. And one of the features is that the keys are no longer, so for curves, usually the keys are like the point on your curve. In ED25519, all bit patterns that are possible are valid keys. I'm not completely sure how he's accomplishing this. My guess is that he starts with a particular point as his generator point, and then the key is, in fact, the exponent that's being used.
That could be. I haven't looked at the algorithm in detail, but
Yep,
it's black magic.
it's black magic. But that's what's going on with that. ED25519 is kind of magic. It's also apparently extremely secure, which is not overly surprising.
The big thing about his, as compared to the one that NIST published, is that he fully documented how he created the generators so that there is, because well, all cryptographers are professionally paranoid or they're not a good cryptographer,
Yep.
NIST did not actually document how they generated their curves, and there is opinions that if you don't document how you generate your curves, there can be hidden weaknesses in the curves. And Dan very deliberately said, no, here's how I did it, and here's why I believe there was no hidden failures, because I did this without pre-computing other stuff that might let me reverse engineer it. He was very careful to
Yep.
not have any reverse in there, whereas some of the others may have it, may not have it, but without public documentation on how they were generated, it's unknown as to whether they're truly secure,
And it,
but there's no theory on how you should do
Conspiracy theory. You find that every government wants to bring encryption.
this.
This is the National Institute of Standards and Technology, funded 100% by the U.S. government.
additionally, there are hints that the NSA had something to do with the curve selection for the
Yes.
public curves that are published by NIST.
Yes, in fact, there is documented proof that the NSA had something to do with that. So,
Yep.
in my view, it is very likely that the NSA has a way to discredit and break that encryption.
Yep.
They have a backdoor.
Yes.
Particularly given the recent story that came out on the Crypto AG, Swiss crypto company. They've been building crypto engines since the 50s.
That story isn't even recent. I
Yes.
heard that story like 20 years ago.
I heard it, but apparently the new piece is that it wasn't just that they got the company to put the back door in, that the U.S. and German, they bought the company wholesale, which is how one of the ways they got them to agree to it, is they
Doesn't surprise me.
through a third parties, they actually own and control the company. And but I guess that's the recent documentation that came out, is that it wasn't just they went over and asked the company, please be nice to us. Years later, they said, yeah, well, you're doing good work.
Yeah, we kind of are the company.
And bought the entire company through hidden third-party proxies so that they would stay bought or stay friendly to the U.S. government and the German government.
Yeah.
So,
So does anybody have any questions about the talk or what I just presented about why things are the way they are, how it works? You look like you're confused but don't know what to ask.
Yeah, my math is not quite strong enough to grasp all of the implications and conclusions of what you're talking about. A lot of this stuff I'm just like encountering for the first time. So yeah, I have a lot of questions, but they're not relevant to actually what you're talking about.
Okay. Fine. I'll end here then. And I'm not sure if another